Thus far, we have spent time discussing a variety of approaches for designing recommendation systems. Today, we shall put our learnings to practice. We shall do this by means of 3 case studies. We'll design a recommendation system for recommending movies, just like Netflix, design recommendation system for recommending songs, just like Pandora or Spotify, and we shall design recommendation system for recommending products, just like Amazon or Wayfair. First case study, movie recommendations. We shall start by discussing recommendation system design for movies. For this case study, we shall utilize Movie Lens dataset. This dataset is freely available at grouplens.org. This dataset has been collected between 1995 till January 2016 at a website hosted by University of Minnesota as a part of a research project. The dataset is a collection of ratings for movies by users. The total number of movies are a little more than 11,000. The total number of users are a little more than 30,000. In principle, each user can assign a rating between 1 to 5 to each movie. Therefore, total number of ratings can be a little more than 330 million. In the data set collected, we have less than 3% of these 330 million or so entries filled. That is, it is an extremely sparse matrix. The goal of a recommendation algorithm would be to fill in these 97% or so missing entries. Among the ratings revealed by users, the distribution of ratings is as follows. Around 4% of entries are rating 1, 10% or so are rating 2, 30% or so are rating 3, 35% or so are rating 4, and rest are rating 5. That is, roughly 20% are rating 5. It is worth noting that a good fraction of ratings are 3, 4, or 5. Less than 15% of ratings are either 0 or 1. However, there is enough variation in the distribution that a simple recommendation algorithm will not be able to get accurate predictions for missing entry. Now, we shall apply various algorithms we have learned to this dataset and evaluate their performance. To be able to evaluate performance of an algorithm, we will need to know how well does an algorithm predict an unknown entry. Now, if entry is unknown, then we will never know how good is the prediction. This is a standard dilemma all such evaluation tasks face. To overcome this, a simple but clever solution has been developed, which is known as cross-validation. We take the available data, hide a small fraction of it from the algorithm, and then ask the algorithm to predict the values of hidden data, and then compare performance of the algorithm by comparing it with the hidden ground truth data. In experiments to follow, we shall hide 20% or 1/5 of the data and use remaining 80% for training. The choice of this 20-80 split is done at random. To evaluate the performance of the prediction, we shall utilize the metric known as root mean squared error, or RMSE for short. It is the square root of the average of the squared error between the predicted ratings and the true ratings. For example, suppose algorithm predicts ratings for position 1 and 2 as S1 and S2, but suppose the true ratings were R1 and R2, then the RMSE is computed as follows. First, compute the summation of the squared difference between S1 and R1 as well as S2 and R2. Now divide this by 2 and then take the square root of it. Now we are ready to consider different recommendation algorithm on this data set. To begin with, and to set the baseline, let us start with an algorithm that does not utilize any data, a random recommendation algorithm which chooses any of the 5 ratings at random and does a prediction. Let's try to understand how well will this algorithm perform on our data. The algorithm will predict a rating to be 1 with 20% chance, or probability 0.2. As we discussed earlier, as per rating distribution, the unknown rating is likely to be 1 with roughly 4% chance. That is, the error will be 0 when predicted rating is 1, which is with chance 4%. Similarly, as per the rating distribution, the unknown rating is 2, 3, 4, and 5 respectively, with chances 10%, 30%, 25%, and 21%. And therefore, the expected or average squared error when prediction is 1 will be 0 times 0.04 plus 1 times 0.1 plus 4 times 0.3 plus 9 times 0.35 plus 16 times 0.21. Summed up all, we'll get 7.81. Now this is the squared error when prediction is 1, which will happen with 20% chance. Similarly, when predictions are 2, 3, 4 and 5, the resulting square error, when we did all the calculations just like what we did for second back, we'll get 3.63, 1.45, 1.27 and 3.09 respectively. Therefore, the total average square error under random algorithm is 7.81 plus 3.63 plus 1.45 plus 1.27 plus 3.09. Okay, that's a lot. All divided by 5, which gives us 3.45. And the square root of 3.45 turns out to be 1.85, which is exactly the RMSE of the random algorithm. The algorithm that uses no information about the data achieves RMSE of 1.85. This should serve as a baseline for performance of algorithms that we shall evaluate. We shall start with the first algorithm we had learned, the population average. In this case, for each movie, we shall compute average ratings, and then for a user for which the rating of this movie is unknown, we shall assign this average rating. No personalization. The RMSE, when evaluated for this algorithm, turns out to be 0.983, much better than the random algorithm. So definitely a good start. When we look at the movies or shows with highest average rating, that turn out to be Lord of the Rings, The Return of the King, Lost Season 1, Battlestar Galactica, Lord of the Rings, Two Towers, Arrested Development Season 2, and so on. Clearly, these are not personalized recommendations as they are based on population averages. Now moving on to personalized algorithms. We shall first look at collaborative filtering algorithms. Using the user-user collaborative filtering algorithm, we find that the RMSE is 0.85. This is down from 0.983 of the population averages. A major improvement due to personalization. To see how it personalizes the movie recommendation, consider the following scenario. Suppose I have rated Love Actually 5, Notting Hill 4, Pretty Woman 4, Sleepless in Seattle 5, Forrest Gump 4, and An Affair to Remember 4. Clearly from these ratings, you might say, I really like romantic movies. Now we can ask the collaborative filtering algorithm to produce personalized recommendation for me using the rest of the movie lens dataset. It will produce the top recommendation as follows: Titanic, Sex and the City Season 4, The Notebook, How to Lose a Guy in 10 Days, Steel Magnolias. Clearly, these seem to be a good fit for the profile of a romantic character. We might want to quickly compare performance of other algorithms as we had discussed. The variation of collaborative filtering, which is the item-item collaborative filtering, when applied to this dataset results into RMSE of 0.91. This is a poorer performance compared to user-user collaborative filtering, but definitely a step up from the population level algorithm. Finally, we can also compare performance of matrix factorization based algorithm. These are based on viewing the user movie rating matrix as having low rank structure, and the goal is to find this low rank structure based on the partially filled matrix. A popular implementation for such a problem is known as the soft impute algorithm. Using this algorithm for the dataset results into a little higher RMSE compared to the collaborative filtering algorithm. So in summary, for movie recommendation based on movie lens dataset, the best algorithm seem to be user-user collaborative filtering, which seem to achieve a very good level of personalization.